Hello, we are José Mendes and Gonçalo Carito. We are introducing Brute Force in Quantum Computers, Chapter 21 of Advances in Financial Machine Learning by Marcos Lopez de Prado. For viewers' clarity, we have some glossary terms which will be defined in speech bubbles within their corresponding slide. If you wish to pause the video to read them, feel free to do so. Otherwise, there will be a glossary of terms at the end of the video. Motivation. Discrete mathematics appears naturally in multiple machine learning problems, including hierarchical clustering, grid searches, decisions based on thresholds, and integer optimization. Sometimes, these problems do not have a known analytical closed-form solution, or even a heuristic to approximate it, and our only hope is to search for it through brute force. In this chapter, we will study how a financial problem intractable to modern supercomputers can be reformulated as an integer optimization problem. Here we have the definition of brute force.
Combinatorial optimization problems can be described as problems where there is a finite number of feasible solutions which result from combining the discrete values of a finite number of variables. As the number of feasible combinations grows, an exhaustive search becomes totally impractical. What makes an exhaustive search impractical is that standard computers evaluate and store the feasible solutions sequentially. But what if we could evaluate and store all feasible solutions at once? That is the goal of quantum computers. Here on this bubble, you can understand better what it is quantum computing. The bits of standard computer can only adopt one of two possible states, 0 or 1 at once. On the other hand, quantum computers rely on qubits, which are memory elements that may hold a linear superposition of both states. This property is what makes quantum computers ideally suited for solving NP-hard combinatorial optimization problems. Note this problem is particularly relevant to large asset managers, as the cost from excessive turnover and implementation shortfall may critically erode the profitability of their investment strategies. You can also find on this bubble a better definition of quantum superposition, which you can read. Here you can find the definition of NP, and here concretely what are the NP arguments.
The objective function. We will now see how a dynamic portfolio optimization problem, subject to generic transaction cost functions, can be represented as a combinatorial optimization problem, tractable to quantum computers. Let's consider a set on assets X with returns following a multivariate normal distribution at each time horizon H with varying mean and variance. However, not identically distributed through time. We define a trading trajectory as n by h matrix with little omega. That determines the proportion of capital allocated to each of the n assets over each of the h horizons. At a particular horizon, we then have a forecasted mean mu, a forecasted variance v, and a forecasted transaction cost function tau in relation to h, each of them, and tau in relation to little omega. This means that given a trading trajectory little omega, we can compute a vector of expected investment returns R defined with this formula. The transaction costs associated with each asset are the sum of the square roots of the changes in capital allocations, rescaled by an asset-specific factor, C, in relation to H. That changes with H. Thus, C in relation to H is an n by 1 vector that determines the relative transaction cost across assets. Continuing, the Sharpe ratio associated with R can be computed with this formula as seen, mu being net of the risk-free rate. Here we also have a bubble that allows you to read the definition for Sharpe ratio to give better understanding.
The problem that we have at hand is the following. We would like to compute the optimal trading trajectory that solves the problem of maximizing the Sharpe ratio so that the sum of all values of the trading trajectory matrix omega equals to 1. This problem attempts to compute a global dynamic optimum, in contrast to the static optimum derived by mean variance optimizers. If you want to know better what are mean optimizers, please read this bubble. Note that non-continuous transaction costs are embedded in R. An integer optimization approach. Compared to standard portfolio optimization applications, this is not a convex, quadratic programming problem for at least 3 reasons. The first is the returns are not identically distributed because the mean and the variance change with the horizon h. The second is because the transaction costs, which is a tau that we saw before, are non-continuous and also change with the horizon h. And finally, the third is that our objective function, the Sharpe ratio, is not convex. Our solution strategy is to discretize it so that it becomes amenable to integer optimization. This in turn allows us to use quantum computing technology to find the optimal solution. You can also see on this bubble better what it means an integer optimization problem.
Pigeonhole partitions. Here we will see how to calculate solutions without making use of any analytical property of the objective function, hence the generalized nature of this approach. Suppose that we count the number of ways that k, units of capital, can be allocated among n assets, where we assume that k is greater than n. This is equivalent to finding the number of non-negative integer solutions to the units of capital k, which has the nice combinatorial solution shown. Usually, order does not matter in the partition problem. However, for our particular problem at hand, order is very relevant. Given this figure, we can see that, for example, if k is equal to 6 and n is equal to 3, we are capable of getting the partitions 1, 2, 3 and 3, 2, 1 must be treated as different. Obviously, 2, 2, 2 does not need to be permutated. This figure illustrates how order is important when allocating 6 units of capital to 3 different assets. This means that we must consider all distinct permutations for each partition. Even though there is a nice combinatorial solution to find the number of such allocations, it may still be computationally intensive to find as k and n grow larger. However, we can use Stirling's approximation to easily arrive at an estimate, which is an approximation for factorials. It is a good approximation, leading to accurate results even for small values of n. In this snippet, we see that an efficient algorithm to generate the set of all partitions, p to kn, where w are all natural numbers including 0, whole numbers. First, in the code, we import from itertools the function combinations with replacements, which we use in our defined function pigeonhole in order to create combinations between number of assets n and the units of capital k. For each combination, we calculate the formula p to kn, which corresponds to r in the code.
Feasible static solutions. Considering now the pkn, so the pigeonhole that we calculated just before, we look for each partition and we can define them a vector of absolute weights, which you can call omega E, such that the modulus of omega E is equal to each one of the partitions divided by content key, and the sum of all elements of that matrix is equal to 1. These constraints are called the full investment constraints. This full investment without leverage constraints implies that every weight can be either positive or negative. So for every vector of every weight, we can generate two n vectors of signed weights. This is accomplished by multiplying the items in omega A with the items of the Cartesian product of -1 interval with n repetitions. Taking this in account, we'd like to compute big omega, which is the set of all feasible solutions at any given horizon age, which can be described by this formula. In this snippet, we can see how to generate the set big omega of all vectors of weight associated with all partitions, as we just saw the mathematical formula. In terms of our code, we start by importing the Cartesian product function from the library itertools. And we define our function get all weights, which receives as parameters k units and n assets. First, we use the pigeonhole function, which we just defined before. And after that, after having this, we go every partition, and then we calculate this absolute weight vector, which is the big omega. In order to evaluate trajectories, let's then give these vectors omega, which represents all the feasible solutions. So it means that we can define a set of all possible trajectories phi as the Cartesian product of our omega with the h horizon repetitions. Then, for every trajectory, we can evaluate its transaction costs. The object params, which you can see here in our function, is a list of dictionaries that contains the values of the asset-specific factor, C, the mean, mu, and the variance, V. We define then a function where for each trajectory, W, which corresponds to our mathematical formulation of omega, we then compute the transaction costs. Now, for every trajectory, we can also calculate its sharp radio. This time, we define a function called eval SR, which receives the same parameters, params, as defined before, and where we can evaluate the sharp radio for multiple horizons. For that, we go through each horizon edge, and we calculate the mean and the covariance matrix as defined in the SCR formula we saw before. We can then, having this calculated, we can, for every trajectory, select the one with dynamic optional performance. And considering, again, the params, which are the representation of every trajectory possible defined in phi, we start by generating first the partitions and creating the partition matrix. Secondly, for every trajectory W, which it was the omega in mathematical formulations, we calculate the transaction cost and the SR with the formulas that we just saw before. And with that, we find the smallest SR, which is the one that shows us that corresponds to the trajectory with dynamic optimal performance. Finally, let's consider that this was actually an unconstrained portfolio optimization problem. In this case, for every trajectory, we'll want to select the one with a static optimal performance. For that, we could use this function where we'll only use the variance, so the covariance matrix as an argument, and also A here, which is the mean of every trajectory. And then we invert the covariance matrix and we'll do the inner product and with the mean in order to calculate the trajectory W with static optimal performance. In sum, this procedure selects a globally optimal trajectory without relying on convex optimization. A solution will be always found, even if the covariance matrices are ill-conditioned, if transaction cost functions are non-continuous, and so on. The price we pay for this generality is that calculating the solution is extremely computational intensive. We know that digital computers are inadequate for this kind of problem. And so we need quantum computers because they can evaluate multiple solutions at once, and then they can solve this problem. The approach set the foundation for Rosenberg et al., which solved the optimal trading trajectory problem using a quantum annealer. This same logic can be applied to a wide range of financial problems that involves path dependency, like the trading trajectory that we observed. To learn more about what is convex optimization, you can read the description on this bubble. If you want to understand what NP-complete problems are, you can also read this description. If you want to understand better what is quantum annealing, we also have this description which you can read.
Here we have a numerical example where we are going to create a random matrix and generate the relevant parameters in order to evaluate the performance of our functions that we created previously. Being an example of a function that can be executed by a digital computer versus one that requires quantum computing. A quantum computer would evaluate all trajectories at once, whereas the digital computer does this sequentially. In this image, we can see the differences. A quantum computer can calculate with qubits, which represent 0 and 1 at the same time, whereas classical computing, with transistors, it calculates, which can represent either 0 or 1. Power increases exponentially in proportion to the number of qubits when you're dealing with a quantum computer, whereas classical computing power increases at a ratio of 1 to 1, this being with the number of transistors. Quantum computing, however, does have high error rates and needs to be kept ultra cold, whereas classical computers have low error rates and can operate at room temperature. Quantum computing is well suited for tasks like optimization problems, data analysis, and simulation, whereas classical computers are mostly suited for everyday processing. Here, we have a snippet of script that will return a random matrix of Gaussian values with known rank, which is useful in many applications, and that we will use for our current purpose. This snippet generates our parameters: horizon, h, vectors of means, mu, covariance matrices, v, and transaction cost factors, c. These variables are stored in a params list. This snippet computes the performance of the trajectory that results from local static optima, which can be performed on a digital computer. We iterate sequentially over each trajectory in order to find the optimal static Sharpe ratio. This can take time, but it's something which is accepted for digital computers. On the other hand, this snippet computes the performance associated with the globally dynamic optimal trajectory, applying the functions explained throughout this video. With this solution, we are looking at all trajectories simultaneously, only possible with quantum computing. From here, we have our glossary of terms that you can look at and review the definitions defined in the bubbles throughout the video. To conclude, we have our bibliography, which can be found as our references of things throughout our video, one of which being the Rosenberg et al. And with that, we conclude our presentation. Thank you very much.